So today we are studying about the systems and their classification. So first we study about the definition of the system. What is a system? And how the systems are classified based on their attributes, based on their several properties. So that is what we are going to look into today. And these are the sources. So let us define a system like this. System may be viewed as an interconnection of operations. Basically, system is nothing but an interconnection of operations. Interconnection of operations means, I say in a different way, I say just a set of operations. It is a set of operations either in cascade or in parallel. Okay, the set of operations may be implemented serially or parallelly. Okay, so because we are using serially parallel connections both, that's why we call here as the interconnection of operations. Okay, so instead we can say that set of operations implemented either serially or parallelly or in parallel or both to transform the characteristics of the input signal. Okay, so input signal has certain properties and I want to modify at least one property of this input signal. Okay, so at least one property of this input signal, if I modify, I will get a new signal, that is output signal. It need not be changing of all properties. At least one property, if I say I can change by the set of operations, then I can view the set of operations as the system. So what is the definition of system? System is the set of operations performed either in parallel or in serial to modify or manipulate at least one property of the input signal to get a new signal. That is what is. And the operator used to denote this set of operations is H, capital H. So when I write y of t equal to h of x of t, what it means is the system is operating on this input to give the new output y of t. Okay, so similarly for discrete time case, I have y of n equal to h of x of n. Now let us take one example. Here I am showing a system H. What it is doing? It is taking nth sample of the input and it is delaying the nth sample by k units. Okay, it is basically delay. N minus k means delay. And same thing, the operation, what is the operation? Set of operations I am doing here, that is delaying operation. Okay, delaying by k units, k time units or k indices. So that I am representing as s to the power k. Okay, so this is the set of operation and where s is the discrete time shift operator. When I have s to the power of 1 means when k equal to 1, s to the power of 1, it is single shift operation. That means one sample delay. If it is two sample delay, k equal to 2, so I get s to the power of 2. So like that, kth shift means s to the power of k. So that is the operation, that is the notation I am following. Now consider a system given by this equation. What is this equation? The nth sample means current sample of the output is given by 1 by 3 multiplied by sum of 3 samples. What are these 3 samples? First one is the current sample, previous sample, second previous sample. So if I add these 3 and divide by 3, basically this is nothing but averaging of 3 numbers. Averaging of 3 numbers, 3 input values or 3 samples. Okay, so that is the overall operation which is expected here. In terms of shift operation, how we can represent this one? This is no shift. So here 1 is there. Here n minus 1, 1 shift, s to the power of 1. Then here 2 shifts. In this case 2 shifts. It is represented by s to the power of 2, s square. So this is then h equal to 1 by 3 multiplied by 1 plus s square. So this is what is using the shift operation, I can express the system in this way. Now, pictorially, if I want to represent this, how I will represent? So, x of n, current sample is directly fed to the multiple summation here, because this is the summing device. Because I have addition of 3 terms. So, 2 additions are there. So, those 3, the 3 additions basically including 1 plus s square. Okay. So there are 3 terms I am adding. So this is the summing device, sigma summing device, and x of n is directly coming because it is multiplied by 1 here, and second one s into input. Okay, s into input means x of n minus 1. So that is 1 delay. This is 2 delays. That is x of n minus 2. So what I have here after this, I have x n minus 2. At this point, I have x n minus 1. Okay. Then this is x n. Okay. This is x n. So all 3 added. Then finally scaling operation, multiplication operation. So it is multiplied by a factor of 1 by 3. So I will get the output. Okay. So I have given the functional representation in terms of expression. I have given the representation as a block diagram, and I have given the representation in the form of block diagram again for the total system, detailed block diagram. Okay. This is what we have. So what it means, this kind of system can be called as moving average system. Why it is called moving average system? So let us try to find let us say x5. Let us say to try to find x of 5. Okay, I'm using instead of square brackets, I'm using small brackets. Okay, it should not matter. X of 5 equal to, this is y of 5. So I will erase this. So output, I want to find the 5th sample, n equal to 5. N equal to 5 means substitute n equal to 5 here. I will get y 5 equal to 1 by 3 x of n means x5 plus xn minus 1 means 5 minus 1 4 plus x 5 minus 3 5 minus 2, that is 3. Okay. So this is what I have. So here what I am doing to get the 5th sample of the output, I am taking the average x of 5 plus x of 4 x of 3 divided by 3. So I am finding the average of 3rd, 4th and 5th samples. Now if I take x of 6, how I will get x of 6? 1 by 3 multiplied by x of 6 current value plus x of 5 plus x of 4. So what is happening here? So now it is the average of 4th, 5th and 6th samples. Like that as you go on. So what is happening here is, see here, I have, let us say I have some samples here. Discrete time signal. Some samples are like this. So let us say this first 0, 1, 2, 3, 4, 5, 6. Okay. Now take first 3 samples, find the average, again shift by 1 sample, again find the average. Afterwards 3rd, 4th, 5th samples, take the average. Afterwards fourth, fifth, sixth samples. Okay. First average, second average, third average, fourth average. So what I'm doing, I'm taking a window of 3 samples, and the window I am shifting towards the right, sample by sample. So that means I am moving the window to find the average value. Hence, the name moving average. That's why this kind of system is called moving average system. Okay. It is nothing but moving average system. So, I have shown the moving average system of window size 3. And this is what I have shown in the previous slide. This is the system operation. Now, in this one, I require one delay element, and here 2 delay elements, one by one after the other. Two units delay, 1 unit delay. Total how many delays I want? 3 delays I want. That means if I want to implement this, I have to use 3 delay elements. Okay, 3 unity delay elements. So let us try to optimize this one in a better way. Same system, same relation, same system, and we will implement in a different way. In a cascade manner, at least one path is cascade. So what is that? I am feeding Xn at the input to a single unity delay system, and I am getting X of n minus 1 here. Then what I am doing? Another delay I am putting it here, and again X of n minus 1 is delayed by 1 unit. X of n minus 2 I will get here. Okay. So what I want? I want X minus 2 here. X of minus 1 I want. Xn I want. All 3. Again I will sum here. Again this multiplication I use as usual in the as shown in the previous system. So what is the difference in this case? Here I am using one sample delay, another sample delay. So only 2 delay elements, that is 2 unity delay. Each delay means 1 unit. So 1 sample delay, 1 unit delay or 1 sample delay I am optimizing here. So here only 2 delay elements are sufficient. In the previous one I must have 3 delay elements. So I saved 1 delay element. Okay. But this is because moving average of only 3 samples, you don't find much difference. If I take the window size of 1024, for example, if I take windows of 1024 samples, then it saves 1024 delays. Okay. 1024 delays you will save. Okay. Instead of 3 delays, I am using only 2 delays in this configuration. So naturally, you will save 1024 delays. So as the window size increases, the saving is very significant here. Okay. So that's why basically when we implement in hardware, this is the form which is used. Now let us take another moving average system. What is this moving average system here? I am taking the average of current sample, previous sample, and future sample also. Okay, as I discussed some time ago, this is something related to causality of the system or causal signals also. So something, when t equal to 0, you switched on the function generator. So at t equal to 0, when you switch on t greater than 0, only the function generator will generate the signal. It cannot generate the signal before you switch on the function generator. Okay. So, but in certain cases, in offline processing, so when you have a memory of, you have saved so many values in the memory, and this is, if you have at present, if you have here, okay, if you are here, for example, these are all previous samples. These are all previous. In fact, you are here, I should say. That is the better way. So here you are here. Current sample. The current sample is this. Previous sample. Next previous sample, like that. These are all previous samples. Okay. Now, what about the future sample? The future sample has not arrived yet. Okay. Future sample has not arrived yet. But instead of taking the reference here, if I take the reference here, what happens? This is 0th location. These are previous samples. These are future samples. Okay. So if I change the reference, you can get this kind of thing. Okay. So anyway, forget about the kind of concept here. And here future sample. Mathematically, I am taking the summation of current sample, previous sample, and future sample. So how I represent by our notation? This is current sample 1, delayed sample, 1 delay, single delayed sample, and single advanced sample. Okay, one advancement is the one sample advance, that is here I should say k equal to -1. In this case, the k equal to s to the power of k I have shown earlier, correct? K equal to -1 here. So that's why you will get this system. And of course, this is same pictorial representation, s of -1, s of 1. Okay, so this is another system which uses, and in future we are going to show that this system is going to be called as a non-causal system. Now let us talk about the properties of the systems. So the properties of the systems, there are many properties, and based on these properties, we can classify the system. So by studying the properties of system, we can classify the systems also. So basically this is nothing but the classification of systems. Now let us talk about the stability of a system. First of all, if some system is not stable, means there is no stability. In general, if you talk about any system or anything which is not stable, it is not much useful in practice. Something should be stable. When you say some word, it should be stable on that word. Otherwise, you are not reliable. In the same way, if the system is giving different outputs at different times, okay, you cannot really use that system. Okay, so in that sense, let us define the stability of a system. A system is said to be bounded in, bounded output, BO, stable, if and only if every bounded input results in a bounded output. What is bounded input? Let us take some signal you take like this. There is some signal like this. What is the maximum limit? Mx. What is this side? Minus mx, let us say. Plus mx and minus mx. So between these limits, the signal is oscillating. The input signal will never go beyond the mx. That means the input signal level is limited, is bounded by mx. Okay, so that is what is, and mx is a finite value. So what I will say, this is the input one, for example. So modulus of x. What is modulus of x? I'm not worried whether this mx is on the positive side or negative side. See here there is a less value. This is smaller value actually. This is smaller value. Let us say, so this side it is, so okay, fx, I will take fx only. So this is smaller value. This is larger value. So I will take the larger value. So whether it is occurring on the negative side or positive side, doesn't matter. It is the amplitude of the signal I am taking, absolute value of the signal I am taking, and that is bounded by a finite value, that is mx, which is less than infinite. Means less than infinite means it is a finite, and it is for all t. This is more important, for all t. See here, what is the x-axis? T is the x-axis. T on the x-axis, x of t on the y-axis. For all t, that means the signal may be extending up to infinite, but still at any instant t, in future also, it cannot go beyond the bounded mx. Okay, that is the meaning of this one. So now if the x is bounded like this, y is also bounded. That means the system gives a maximum output. The system cannot give an output beyond my. There is a limit on the output also. Okay, so for a bounded input, I will always get bounded output. But mx and my may be different. They need not be same. They may be different, or they may be same also. Doesn't matter. But these are finite positive numbers. Numbers means real numbers. In general, you can take it as a real number. You should not think that it is integers or whole numbers like that. Okay, so it is decimals, all decimal numbers, whatever. If you want to say 2.5, 2.5678 volts, 2.7655 volts, like that. Okay, so but the mx and my need not be same. Now, same system, whatever I have taken, I have to show that this is BO stable. Okay, so what is take the equation, take the absolute value on both sides. I have absolute value of y equal to absolute value of total summation here, total term. Because 1 by 3 is a constant, I am taking it out. Now each term I have to take absolute value. Now if I take absolute value, actually this is equality sign. Basically this is equality sign. Then so in place of x of n, I am putting the bounded value, maximum possible value. Then here also maximum possible, because for all n it is true. So for second term, third term also I am putting mx, mx, mx. The moment I put the maximum value, what I will get, I have to put the inequality here. That means the output absolute value will be less than or equal to this, because this is the actual values are this, and these values are bounded by this. I am substituting with maximum values. So that is maximum value is same for all. That is mx. So 3mx divided by 3, it is equal to mx, and the output will not go beyond mx. That means here both mx and my are same here in this case. Okay. So this is what. So output is also bounded by some constant value, that is mx. Hence I can say that it is stable. I can say that the given system is BBO stable. Take another example. This is the discrete time system. Here I am using n and x. Signal is given by y of n. That means output of the signal. Output of the system is given by y of n output equal to r to the power of n x of n. Okay. Where r is greater than 1. Here it is shown as r is greater than 1. Show that this system is unstable. This is a unstable system. We have to prove that. So this is what is input condition. We are assuming, because bounded input, correct? Bounded input means even though it is not given in the problem, you have to assume, because you told that it is a, we should say that, and I can also say that where input is bounded. Okay, we can say that input is given, that input is bounded. If input is bounded, so this is the maximum limit is mx here. Then take as usual the absolute value on both sides. So this is r to the power of n. Why? See, r to the power of n is not constant, because the function of n is the subscript here. So it is dependent on r to the power of n. R to the power of n is also dependent on n. So both terms are dependent on n. So nothing is constant here. So both terms you will get the absolute value. And so this is, what is this one? This is, so this I can write as absolute value of r to the power of n multiplied by, what is this? This is nothing but mx. This is nothing but mx. Okay. So what about this? If this is bounded finite, if this is finite, automatically these two terms will be finite. Okay. Because mx is already finite, this should also be finite. So for all values of n, now if r equal to greater than 1, let us say 2, r equal to 2, let us say r equal to 2, then r to the power of 1, n equal to 1, 2, then what I will get? R to the power of n equal to, I will get 2 square, 2 cube, 16, like that. So 2 to the power of 1000, 2 to the power of 10,000, like that it will go on. Now, if r is greater than 1, okay, if r is less than 1, let us say 0.5 to the power of n. What I will get? First 0.5 square, 0.25, okay, cube. So that cube is nothing but 1 by, so this is 0.5, 5 is 25, 25 is 125. That is 0.125. Okay, 0.125. So what happens is, when r equal to greater than, output is increasing, R to the power of n is increasing like this. When the R is less than 1, it is decreasing like this. So when R is less than 1, it is decreasing like this. So it can be called as a stable system, because it is a finite. Ultimately, is going to 0 is also a finite. So it is not escalating. So here, when R equal to greater than 1, it is escalating. It will finally go to infinite. So the system is unstable. Okay. So the given system is unstable. That is what we have to derive. Okay. So what about the next classification? Memory. A system is said to possess memory. It is a memory system with memory, if its output signal depends on past or future values of the input signal. Okay, past or future values. It has a remembrance of future values, remembrance of past values. Okay, future values anyway, as I explained to you earlier. So you have to consider in that sense. Now, a system is said to be memoryless if its output signal depends only on the present value of the input. Okay. Here in this case, output signal depends on the past and future values. Here the output signal depends only on the present value of the input. That means y of n depends only on the x of n. Okay. In terms of discrete signals, y of n is dependent on x of n only. It is not dependent on x of n minus 1 like that. Okay. If it is memoryless. If it is memory system, it is dependent on all previous or future samples. Now take an example. Take a resistance here. I am taking a resistance. I want to find the current in this, flowing in this, and I have given an AC voltage source. I have connected AC voltage source here. So I of t equal to I equal to V by R. I equal to V by R. R is a constant resistance. Okay. So what it means is, at any instant of t equal to t1, then at t1, if I take V of t1, I have I of t1. That's all. Okay. So at the same instant, the whatever voltage is existing here, that is the thing which is influencing the current at the same instant. Okay. That's why it is called memoryless system. What is memory system? If I take a memory system, take an inductance like this. Again, let us try to find the current. Then you have to give a voltage again here. V of t, again same voltage, AC voltage. Okay. So this is inductor, which should be varying with respect to time. You cannot use the DC voltage. You cannot connect a battery here. Okay. So it is an AC source. I have inductance L, and it is given. What is the expression for current in an inductance? I of t equal to 1 by L. 1 by L. Integration from a minus infinity to at this instant, current time. T is, because we are considering I of t, means tth instant. So up to t, all minus infinity up to t, you have to integrate the voltage. That means this current is dependent not only on the voltage at current instant, it is all previous, the history of the voltage, all values which have occurred earlier, you have to integrate to get this current. That means this current is dependent on the all previous history of this voltage. Okay. So for example, if I take let us say some voltage is like this. I want to find the current at this instant. I want to find the current. Okay. This is current waveform. This is voltage waveform. Okay. I want to find current here. So what is the instant here? This is the instant here. I want to find the current at t equal to t1. Let us say this is t equal to t1 instant. I want to find the current. Then all the history of this voltage, I have to consider to find this value. Not only current value. This is the current value. It is dependent on this current value. It is also dependent on all previous values. This is called memory system. Okay, system with memory. So inductance and capacitances, they have the memories, whereas the resistance has no memory. Causality. A system is said to be causal if the present value of the output depends only on the present or past values of the system. Okay? Present value and all previous values. It is not dependent on the future values. Okay? So then you can say that it is a causal system. We have discussed it several times about causal signals previously. Okay? So what about the other thing? If it depends on one or more future values, then the system is called non-causal system. At least one sample, it is taken from the future. So it is non-causal. You cannot really realize the system, that kind of system in real time. You cannot realize that system in real time. So what is an example here? This is causal system, correct? This is causal system, all current values and all previous values only. Then what about this? One future value is there here. Okay? So causality is required for a real time. This system I cannot implement in real time. Okay, I have to store all the values, then change the reference, then I can call that as a non-causal system. Offline processing may be possible in this, but causality is required. Non-causality is if you have any non-causality if the system is non-causal, you cannot implement the system in the real time. It requires causality. Okay. So thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.